which which I which I cannot do right now because I don't have the Excel. I only got the book. And I follow all your steps in the previous cases. I also found the entropy. I used the constraint just exactly like what you show in the slide. But instead of getting the result like 17, 8, and 5, I got 11, 11, and 11.
Oh, 11, 11, 11, that means I think maybe you set different constraint because.
But I already set the constraint, the sum must not exceed 30. Yeah, we'll just see later. Yeah. Okay.
Let me check.
Okay.
It should be equal, not less than. It should be equal, I think.
Equal?
Yeah, equal.
No.
I put equal.
Where did I put that file? Is that maximum entropy, right?
Yeah. Yeah, maximum entropy.
Maximum entropy and then queuing. Is this the one? Let me share my slide with you. Let me share my screen, okay? Is this the one?
Yeah, I think so. Yeah.
So we want to find what do we want to find in this case? So this is the server 1, 2, 3. Service time.
Service time.
And then
we need to find the number of customer in 30 when one batch come, we got 30 people, how to distribute it, right?
Right. And then what do you want to get is you want to get the
so first we
calculate the number of
calculate the probability first.
Yes, how do you calculate probability?
So it's n over the sum.
Okay. So this one I put R, correct? Can you see it?
Yeah, that's n times R, yeah.
N times R, okay.
The same with that one.
Yes, and then this is the probability. So this is divided by that. So getting C5 divided by F. Okay, and this is your objective. So in this, I calculate the total entropy. And then, the queuing time is this one. Within all of this, correct?
Okay. Oh, wait, yeah, I stop until the entropy because I confused what I need to do next.
So then let's do the solver.
Okay.
So here I want to maximize the entropy. Where is the entropy? Here is the entropy. Then I change the variable N1, N2, and 3. Total 30, and then you want to put it integer or not. So if you want to put integer, so you can say that this N1, N2, N3 are integer.
And underscore is the total, right? For the
Yes,
customer. Yeah.
correct,
Okay.
correct. So if you don't want, so you can remove this 3. Okay, so let's solve for integer first. I found the solution. So yes, the probability is almost the same, right? And entropy ratio is about almost 100%. So if we remove the integer, I delete this, huh? And I solve again. Then of course entropy ratio is 100%. The one is equal is the probability, right? But the one has the customer, of course, not the same. This is 16, 8, and 5.
Oh, yeah. Okay. I think I already understand where did I went wrong. Okay. Okay. Thank you, sir.
So in maximum entropy, what you will get is equal probability, right?
Mm-hmm.
But your goal is not to get this. The one that you want is actually this.
Yeah. Okay. Okay. Thank you, sir.
Correct, right? Good. So okay, let me see this. I have a couple of announcements. So first, don't forget your recitation. Okay, so you need to fill in the recitation because this is quite good point for your grade. And we have only 2 more lectures today and on June 8th, right? So on June 8th, you will present your final workshop. And then, okay, this is the link in Moodle. Can you see it? Okay, and then you also need to send your final project submission and the paper submission based on the course syllabus. Okay, and our last lecture in June 8th will be the 2 of them, integer programming and dynamic programming. So we have very limited time. Please read beforehand. So today our topic is about IFN, ideal flow network. So you can download this Excel add-ins here. Okay. So once you download, then you can double click this and it will install to your Excel. This is a program. Are you okay?
Sir,
Yes.
is there any add-ins for Google Sheets?
Sorry, no.
Is it available on the internet?
Yes, it's available in the internet, but the one that is available in the internet is the old version. I think it's version 2. The one I gave you is version 5.
Oh, okay.
Okay, so let's start. Okay, so my slide I did not share. Okay, so today, good morning everyone. So today we will discuss about ideal flow network. Okay, so this is part of my research, and you have learned about maximum entropy, you have learned about Markov chain. So this is like the continuation of that. And you also learn about queuing theory. So again, this is also the continuation of that, right? Okay, so before I introduce what is ideal flow network, okay, I would like to give an overview that today we will discuss about random cycle, random walk, and IFN with the cloud node, equivalent IFN. Then the computation, I will just make it very brief, so you can use the Excel add-ins that I give you, and there are many other software of IFN that are available over the internet. And then I will discuss about calibration and briefly about application, only in transportation, but I can also briefly discuss about application in data science. Okay. Okay. So there are many types of IFN. Okay. The basic IFN is just the D graph, and there are many special cases of IFN that we will not discuss in this class. Okay. So dual IFN, complex IFN, functional IFN, we will not discuss in this class. So we only discuss basic IFN in this class because we have only 3 hours to finish, okay? So let's start with the game. So you can create any network, okay? So randomly you can create any network. Say you create a network of 5 nodes, 7 links, okay? The only requirement of that network is you can start from any node, okay? And to go to any other node, don't forget that you can go back to your origin. So what's the meaning? This is a strongly connected network, okay? So from your home, you can go somewhere and then can go home. Okay. Then you can set random path from your home node to any other node and then find another path to go home. So this is to form a random cycle. And then you record the trajectory path of each link by tallying the count of the flow on each link. Okay? And then you do that several times until all links has at least one trajectory pass through it. Okay? Now, after that, you will put the tally of the flow into a matrix. So my question to you is, what happened to the sum of rows and the sum of columns? Do you get it? So, okay. You will create a flow matrix eventually. Okay, so flow matrix represents the number of trajectories that pass through the corresponding links. Okay, and what is trajectories? Trajectories is defined as follow. So, suppose you have k nodes. Okay, so V1, V2 until Vk, and then now there exists 8 is the index of the node, okay? So that when you have Vh equal I, then Vh plus 1 equal j. Then the meaning is there is a direct link between the 2 nodes. Okay? So when you create the node with a direct link with an arrow, okay, and the trajectory will pass through all this direct link, and then you count this, it will become flow matrix. Still abstract? Okay, so once you have the flow matrix, all you need to do is to divide the flow matrix with the sum of flow matrix, then you will get stochastic matrix of Markov chain. Okay, I'll give you an example. So this is the flow matrix. Okay, and then you divide each row with the sum of each row. Can you see it? For example, 2 divided by 4 is 0.5, right? 2 again divided by 4, 0.5. Okay, 3 divided by 3 is 1, and so on. So 4 in here in node T, 4 divided by 5 is 0.8. Okay, 1 divided by 5 is 0.2. Okay, so you can see from the flow matrix, you can find the stochastic matrix, which you can use for Markov chain. Okay. Now, ideal flow network is easy. Okay, from the stochastic matrix of Markov chains, you want to get back the flow matrix. That's it. Okay, so if you notice the flow matrix here, the sum of rows is exactly the sum equal to the sum of column. Can you see it? Okay, the sum of row is 4, 3, 5, 5, and then the sum of column is also the same 4, 3, 5, 5. Okay, let's try. Let's practice. Okay. So suppose you want to assign the following trajectories into the given network. Okay, so you have 4 nodes. How many links? 1, 2, 3, 4, 5, 6. 6 links. So let's define, say, any number of trajectory, but I give you here the trajectories, which is number 1 is A, B, C, A. Okay. Number 2 is B, C, D, B. Or if you look at all this trajectory, you will see that they are actually the first node and the last node are the same. So it means it will create cycles, right? So this is a random cycle. Let's say you have A, B, C, A. What will happen? So if you have A, B, C, A, so you go from A to B, right? And then B to C, and then C to A. Then you put 1, 1, 1 there. Can you see?
Yeah. Yeah.
Yes. Okay. Let's do it in let's do it in whiteboard. Okay. You draw for me. You tell me what is the one in the slide so that we can put in the whiteboard. Can you? So we have A, B, C, and D, correct? And this is the link that you have. Okay, tell me the trajectories. Anyone? The first trajectory, what is that? Can you read?
BCA.
Eh?
ABCA.
A, B, C, A. So A, B, right? So
Yeah.
A, B, C, A. Huh? So A, B. So you first A, B, I put 1 here. And then C, right? So I put 1 here. And then C, A. Okay, I put tally here. What is the next trajectory?
BC.
BC. BC.
E.
Oh,
DB. BCDB.
BC, DB, DB. Okay. So let's go from B to C. So I tally another one here. And then what? CD. So I tally 1 here. And then DB. So I tally 1 here. Okay. Next, what is the next trajectory?
CBCABC.
C, B, C, A, B, C. Oh, it will come back 2 times. Okay, let's go. What? CB, right? Where is CB? Here. So CB, 1. And then, what is next?
BC,
BC, so I put 1. Next,
CA,
CA here. I put next,
AB,
AB, and then next,
and BC.
BC. Okay, let's finish. What's the next trajectory?
CD, BC, ABC.
CDB,
CABC.
CABC. Is that correct? Okay, let's do. So first is CD, where is CD? So you got 1, and then DB, right? And then BC, BC, and then what?
CA,
CA. Next,
AB, and BC.
B. Next, BC again.
Yeah.
Okay. Is that finished or still have? There any other trajectory?
Yeah, there's still 2.
Okay. What?
D, B, C, B,
D, B, C,
B, C, A, B, C, D.
C, A, B, C, D. Okay, let's do that. So D, B,
D, B,
so I put 1, and then
D,
B, C, right?
C, B,
And then C, B, and then
C,
what? After C, B, what?
B, C,
Okay, B, C, and then
A,
C, A, and then
C, A, B,
A, B, okay, and then
B, C,
again, right? And then C, D. Okay, is that other trajectory or finish?
there's 1.
There's more one. Okay, one more. Okay, what's the name?
A, B, C, D,
A, B, C, D,
B, C, A.
B, C, A. Okay, let's do it. A, B, right? And then B, C, and then
C, D,
C, D, and then
B,
E, B, and then
B, C,
C, 1, and then C, A, correct? C, A. Okay, so can you make a matrix of this now? So I have A, B, C, D. So A, B, C, D. Okay. A to A, nothing. A to B, how much?
5.
5. And then, is there anything else? B now. B to C, how much?
How much is that? 11? Wait.
B to C is 11. Okay. And then B to somewhere else, nothing. C. C to B.
C to A is
C to
5.
A. Yeah. C to A is
5.
and then C to B is
2.
2, and then C to
D, 4,
2. Which one?
4,
4, right? And then D to
B,
B is how many?
4,
4. Okay, and you sum now. So the sum is 5, 11, 6 plus 5 is 11, and then 4. How about the sum of columns? 5, this is again 11, 11, and 4. Oh, look at the sum. They're exactly the same, isn't it?
Yep.
Row is equal to the sum of columns, right? So this is called pre-magic. You know magic matrix, right? So this is not exactly magic matrix, but this is called pre-magic, okay? Where the sum of rows is equal to the sum of columns. So you see you have a random cycles, and if you do a random cycle in a strongly connected network, you will always get a flow matrix that is pre-magic. That's the lesson. Is that clear, or you have a question?
Maybe how if the sum is not equal, can we still solve it?
If not equal.
The sum of the column and the row is not equal, can still we solve it?
No. It's the result is always equal. That is
Okay.
when your node, and you can try on your own, create your own.
Mhm.
Try you create your own network, random network. Okay, and then you try to do exactly the same like this. We just practice, and magically it will always equal. That's why it becomes theorem. You see?
Okay.
Okay, so because it will become, surely it will always become equal. Okay, that's why this is important, because it will always equal. Okay. Okay, I will show you. So in its assignment, the flow matrix is always pre-matrix. Okay, the sum of row is exactly equal to the sum of column. That's why this is important, because using this technique, you will always get equal sum of row equal to the sum of columns. Okay, so if you add more data, look at this is the data is trajectory number 1 until 6, right? And if you get the probability distribution, okay, as you add more data, the stochastic matrix will move. First time is unclear, but the more you have more data, okay, then the stochastic matrix will go towards certain asymptotic value. You remember in maximum entropy last meeting, okay? In the principle, if you don't have data, you can still get the result based on maximum entropy, right? But if you have more data, then your result will become more and more accurate. This is the most important part here. Okay, so what will happen if the flow matrix is a trajectory which is only path, not a cycle? Will the flow matrix remain pre-magic, yes or no? What do you think? Just opinion. Abel?
I think not.
Not correct. It will not. Why its cycle become pre-magic? What do you think?
A cycle can go back to the start, right?
Correct.
Well, a path is only one way.
Correct. So the cycle become pre-magic because pre-magic means the sum of inflow is equal to the sum of outflow. That means the flow are conserved. Okay. In the path, the flow are conserved. In the cycle, the flow are conserved, but in the path, the flow is not necessarily conserved. Next question. What will happen if the network is not strongly connected? Will you still get pre-magic?
No.
Correct, right? So the requirement of ideal flow network is your network must be strongly connected. Okay. Okay, let's go to the next topic, which is random walk on network. So in random walk on network, okay, you have a path rather than a cycle. Say, given a strongly connected network, in each node, okay, you select the available link at constant probability distribution, and then we record the link flow as the sum of trajectories on that link. Say you have, yes, you want to say something? Karim? Okay, so say you have 100 agent, and the agent keep moving until time infinity. Okay, so in this simplified version, the edges have length of 1, and the agent speed is 1. Okay, and what will happen? So A here is the adjacency matrix of this network. Okay, I run using simulation of 200 agent and 1,000 time step, and I check the flow. Okay, and the flow keep increasing based on the number of agent and the number of time step. So if you see the flow only, okay, this is practically useless. But something happened if you divide the flow with the statistic of the flow. For example, if you divide the flow with the minimum of the flow or the average of the flow or the maximum of the flow, okay, then suddenly, okay, the flow will become asymptotic to an integer. And then not only asymptotic to integer, the sum of row is exactly the same as the sum of column, even though they are path, not cycle. Okay, so what's the meaning of this? The meaning is the random cycle can be approached. Okay, the random cycle can be approached using random path if and only if the time and the number of agents are infinity. So this is where the word ideal come from, because it will reach the asymptotic value only if it is infinity. Okay, so the flow itself is actually useless because the flow is increasing, okay, without bound up to infinity. Okay, but when you divide with the statistic, for example, in here I divide by the total flow, look at the numbers, it will not become exactly 8, okay, but it will almost. Okay. So,
Right, so the bottom is divided by 4.3275, or
yes.
what do you say?
In this case, I divided all of the flow divided by 4.3275, right?
Okay.
Okay, and approaching 1, not exactly 1, but like 1.00001, and then or 0.99999. Okay, so the longer you put in the computation, it will approach 1 in the infinity. Can you see this? This is, so what is ideal flow? Ideal flow is basically relative flow, asymptotic value of the steady state, right, of the flow distribution. Can you see that? Okay, so I tried different relationship to the nodes and so on. It doesn't work. Okay, only when we have relative flow. So interesting phenomena happen when you put, regardless the number of H and N or the total simulation time T, when that N times T is very large to fill the network, we have asymptotic value of relative flow ratio or relative node ratio. Okay, and this will become integer. Amazingly, they will become integer. So very interesting. Okay, so when you have the R, for example, you divide by the minimum R or the maximum R or the average R or the total R. Okay, it will become integer. Of course, R should not become 0. Okay, we skip the 1, 0. And again, the sum of row will be exactly the same as the sum of columns. That means the total inflow is equal to the total outflow. The nodes preserve the flow. Okay? So if you want, you can practice this at home. So this is the one that practically you create exactly the same as before. So now, if you look at this here, if you practice this, you will see the flow is not pre-magic, right? Now, even if the flow is not pre-magic, you can still get the stochastic matrix. And then from the stochastic matrix, later on, we will put into the formula of ideal flow network. Then you will get the flow that is pre-magic. Okay, up to here. Tell me, what is the meaning of pre-magic?
The sum of the rows and the sum of the columns are the same.
Correct. Very good, Abel. Okay. So, what is IFN? Okay. IFN or ideal flow network is a steady state relative flow distribution in a strongly connected network. Okay. Where the flow are conserved. So, very precise definition. Very easy, right? So, in short, you can say IFN is a reducible pre-magic. That's all. Okay, so of course the network is either in the graph, directed graph with an arrow, or in the matrix. Okay, so there are many software available. You can download Python. You can also download the Excel add-ins. Also, there is a JavaScript version. Okay, these are the links that you can use. Okay, so the JavaScript version is accessible in mobile phone. Okay, so the question is why we want to use IFN? So IFN is basically a modeling metaphor. Okay, using traffic flow network as a modeling metaphor and name convention, it will make us easier to apply in many other applications. As long as, okay, your network is irreducible or strongly connected, you define your own definition of what is flow, okay, and then basically you have later on we will have the capacity, and the flow divided by capacity is equal congestion. Okay, now as long as the problem at hand can be formulated as flow equilibrium in a strongly connected network graph, then you should consider to use IFN as your modeling tool. So it's not just for traffic. Originally, it was developed for traffic, but now we can use it for many other applications. Okay. So what is the advantage? You can directly get the long-term stable equilibrium, which is the steady state solution. Okay. And IFN is based on maximum entropy principle. The flow is always conserved. Okay. And nowadays people talk about big data, but the question is, if you don't have data, Okay, how are you going to solve it? So using IFN, there is a principle of parsimony in the data that you require only minimum number of data, then you can still use. Okay, of course, the accuracy is not as good as if you have many data. You can also adjust automatically the change in the flow. And using IFN, you can simulate, okay, based on network structure alone. So practically you use topology of the network. It has sound theoretical basis, the mathematics of it, okay, for the network assignment. And you remember Nash equilibrium Pareto optimality in the game theory? It's also related to IFN, okay? So you can directly get exactly the same time, okay, based on congestion. Okay. I will touch this a little bit later. Okay, what's the limitation? Okay, so you cannot use IFN as modern of metaphor if, of course, if the problem is not about system in equilibrium. Okay, if the problem cannot be represented as flow in network, or if the network is not connected. Okay, there are 4 assumptions in IFN that must be satisfied before you can use. Okay, first is strongly connected, closed system. Second is conservation of the flow, meaning a balanced system. Okay. Third is Markov. That means you have stochastic local information. And the last is steady state. That means long-term equilibrium. Okay. So, out of these 4 properties of IFN, which one you already learned?
Irreducible. The
Yes,
network must be strongly connected.
Correct. And
Pre-magic as well, right?
yes, pre-magic as well, right? So next I will discuss optional, what is called cloud node. What happens if your network is actually weakly connected, not strongly connected, right? So if your network is weakly connected, you can still make it into strongly connected network by a cloud node. Okay, so this is an optional modeling tool to connect the sink node to the source node, okay, via what is called cloud node, just to make it strongly connected network. And then later on, you can hide this cloud node and the dummy links. Okay, and the next property that is so important is scaling. Remember, ideal flow is relative flow, right? So that means you can scale up and scale down to produce what is called equivalent IFN. Okay, I will discuss about this. See, this is the scaling is the most important part here. Okay, irreducible is clear, right? So strongly connected component. Okay, from any origin node, you can go to any other destination node, and you can go back to the origin node. There is always path between each pair of node in the network. Okay, so that means transportation network is example of this, communication network is example of this, close relation in group theory is also example of this. Any problems that can be put into a strongly connected network, you can use IFN, right? I think I already discussed this. Okay, anyway, so strongly connected network is the network in the left, right? From any node, you can go anywhere. Unconnected network is in the network in the middle. You see from A, you cannot go to D. Right? There is no link. While the one in C, the one in the right, is called weakly connected network. Okay, so you can see that the network consists of 2 components here. Okay, so which is the source component and the sink component, right? Okay, what is the source component? Tell me. Anyone?
On the right
Correct.
one.
Yes.
Uh,
Right one.
D. Oh, wait, no.
Component.
The right side.
Yes, the right side, which is DCE, right?
Yeah.
Okay. You see the DCE here. Okay, this DCE form a component. That means from D can go to C, can go to E. Okay, and vice versa. Once they go to this left side component, A, B, F, they are trapped there. They cannot go back. So this is a weakly connected network. So if you have weakly connected network like this, so you create a cloud node and then you connect. Okay, then it will become strongly connected. Clear? Any question? So if you have unconnected network, you cannot solve using IFN, huh? But weakly connected, you can still solve by adding cloud node. Okay, so this is reducible. Reducible means you have several components. Okay, so if you cut this network, you will see there are two components. Okay. So tell me now, is this network strongly connected or weakly connected?
Weakly.
Strongly.
Tell me why.
I mean, F and E, you can only go between them if you get.
F and E is a component, that's correct. You're very good. So this is a component. But from F and E, can you go to A?
No.
No. That is a weakly component, a weakly connected network, right? So F and E is a component of sink, right? So this is weakly connected, huh? Yeah. So this is the absorbing class. Okay, so mathematically, how do you test? For example, yes, you can look at it, right? If you just use computer, how do you test that this is reducible or irreducible? Okay, the test is very easy. Okay, you have I is the identity matrix plus A is the adjacency matrix, and then you exponent of n minus 1. What is n? N is the size of the matrix. Eh? This is a square matrix, so and if all the elements in this matrix is positive, no zero, okay, then it is irreducible. Okay. Then if you want to check in the matrix, how do I know that this is actually reducible matrix? Okay. By definition, you need to create what is called permutation matrix, so that the matrix B can be decomposed or you can rearrange so that there is zero here. Okay. So definition of mathematics is quite complicated because you need to find another matrix called permutation matrix. So for me, it's easier to use this formula in the computer rather than finding the permutation matrix, right? Okay, so tell me, this is reducible or irreducible?
Reducible.
Reducible, why?
Because there are some nodes that not connected.
What is that
Weakly
node?
connected.
What is that node therein?
Weakly connected. Sorry.
Yes, weakly connected. So weakly connected is reducible, not irreducible. Irreducible means strongly connected. Okay, so this is weakly connected, so this is reducible. So which are those components that make it reducible?
F and E.
Very good, Darren. Yeah, this is exactly the same as before. Huh? So if you put into the matrix, okay, you will get this. You see there is 0, 0 here. Okay, so that means this is reducible. Okay, the same thing here. Okay, if you calculate the value, okay, of this, you see there is no 0 in this matrix, right? All are positive. So that means this network is irreducible. Can you see that? Is there any 0 in this matrix? No, right? So the test, and you look at the test again. The test, if it is reducible or not, is first you add I and then the matrix with the adjacency matrix, and then you exponent with the n plus minus 1. If all elements are positive, then it is irreducible.
Wait, n is the amount of points?
N is the amount of points, that's correct.
Okay.
So in this case, the number of points is 6, right? Until F, so 6. So that's why I plus A exponent 5. Okay. How about this? Reducible or irreducible?
Reducible.
No? Why? Why, Dari?
Because the right side cannot go back to the right side after go to the left. Like there's two components.
Oh, you're very good. Okay. So this is reducible. So it's weakly connected. And you see here, we compute the test. You see there are some zeros. Can you see this? There are some zeros. Okay. If you put into matrix, okay, and you plus with the identity matrix and exponent 5 in this case, because the number of nodes is 6, right? So you will see there are some zeros. Not all are positive. Okay, so this is, even if only 1 zeros, that means this is reducible. Clear, yeah? Okay, next topic is about pre-magic. Okay, so what is the meaning of pre-magic? System in equilibrium. There is a steady state balance. How do I know? The sum of rows is exactly the same as the sum of columns. That means the sum of inflow is exactly the same as the sum of outflow. Okay? So if you want to put into mathematics, you will have like this. In the matrix, you will have like this. So what is this? A is adjacency matrix. Okay, J is the column of a factor of 1. Okay. Okay. Check if the flow of the following network is pre-magic, yes or no. Can you see it? Is this pre-magic, yes or no? How do I know? Easy. Look at this, okay? In this node, what is flow in? What is
Four.
4.
4? What is flow out?
2
4.
and
2 plus
Yeah.
2
2
is
plus
4.
2 is
So
4.
exactly the same, right? So this is,
Uh,
okay, check. How about this one? What is flow in?
all the same, 3 and 3.
Correct. How about this one? What is, so this is check, right?
5 and 5.
Is that 5 and 5? Yes. So check. How about this?
5 and 5. Oh,
5 and
okay.
so it's pretty much it. Okay.
Okay.
Nodes are balanced. Okay. So then you say this is pretty much it. Okay. So easily you can put them into matrix and you can see the premagic property. The sum of row is exactly the same as the sum of column. Clear, yeah? Okay, next is the concept of cloud node. So the theorem said that the only one cloud node is sufficient to convert the weakly connected network into a strongly connected network. Okay, again, this is optional modeling tool. Okay, so if you want to model an external environment, so say your network is already strongly connected, but you still want to model an external environment outside the system, then you add cloud node. Okay, and if you have a weakly connected network, then you add cloud node to make it strongly connected. Okay, and the cloud node can be hidden after the computation later. Okay, so in principle, you can only compute IFN based on strongly connected network. That's why if you have weakly connected, okay, first you refill the cloud node to make it strongly connected. After that, you get the ideal flow matrix, it is premagic and reducible. Okay, and then you get the other matrices that you want. For example, the entropy, the stochastic matrix, the congestion, and so on. Later on, you can hide the cloud node and the dummy links for better visualization. Okay. So, okay, let's give examples. Say you have this network in the left. Can you see? This is clearly a weakly connected network, isn't it? There is a source node here. There are two sink nodes here, right? So how you say, how I will calculate the IFN? Well, I can calculate the IFN by adding cloud node. You see here? Okay. So, and then I can put any number. So I put 1, 1 in here, 1, 1. Then of course, this is the same, right? So be premagic. So this one must be 1, this one must be 1. Okay, this one must be 2. This one must be 2. Okay, then this one must be 2 also. Correct? Okay, so you can easily calculate. Okay. Okay, so the cloud node is optional. So you can also connect directly the sink to the source without any cloud node. Right, something like this. Is it clear? So in this network, this is an example, okay, of an intersection. Okay, in itself is already irreducible. It's already strongly connected. Okay, but you want to model the external system outside the system. Then you still can add a cloud node here. Okay. So up to here, is there any question? Eugene?
Not for now, sir.
No problem?
No.
Okay, good. So can you practice now? Can you add a cloud node and dummy link, and then can you make it a strongly connected network?
Can I try, sir?
Yes, please. You can, I will stop my sharing so you can
So
share. Okay.
say this is one, and one.
Okay, you add the cloud node somewhere. Say, yeah, okay, you draw a cloud.
Okay.
Okay. Then going there. Okay. And then, oh, yes, two, correct. Two, correct. Oh, two also. Okay, very good, very good. Okay, so the dummy links, you can put them as a dot so that you will know this is actual dummy links. Okay, anyway. Very good, Taryn. Okay, so something like this. Share my screen, huh? Can you see it? So anyone want to try? Can you add the cloud node here and a dummy link to make the network below as IFN? Okay, so anyone want to try?
I'll try. But
Yes, please. Okay. Okay, share your screen. Very good. Abel. Make it larger.
what was the question? The intersection?
There's a simple, okay, network. Yes, like that. And we know that AE is 100, BE is 200, EC is 50, and ED is 250.
The question.
AE is 100, BE is 200. Okay, so you draw a cloud node anywhere else, so you can put different color if you want. Okay, so you
goes
put,
like this.
yes, from there. Okay, and then from C,
Do I do like this?
yes, correct. And then from, yes, very good. So how much? CD, how much?
CD,
Of course, CD is EC, the same, right? So then 50, right? Yes, very good. And then that one is 250, very good. And that, now the cloud 2E is 100, and then the cloud 2D is 200. So you can check in all node is pretty much it, right? Very good, Abel. Okay, so let me share my screen again. So because of the cloud node, can you see the matrix here? So you can fill in, okay, and the total network with the cloud node now become 1,200. Okay. Okay, so someone else, can you practice the T intersection? Anyone? Lilian or Michael? Can you create the cloud node and the dummy link for this T intersection?
Oh, okay, I'll try.
Try.
I'll, sh
Hmm.
I'll share the whiteboard, okay?
Yes, please, yes.
Okay, wait.
So you have 4 nodes, A, B, C, D. So you know A, B, you know B, A, you know C, B, C, and B, D. And then you know also the CB and DB. Okay, you just need to draw the cloud node and fill in the values. Okay, so AB is 100, 1,000.
AB is 1,000.
Right, AB is 1,000.
Okay.
Then BA is 150. So BA is 150, right? And BC is 1,200. And BD is 750. BD 750. CB 500. CB 500.
CB 500.
And then DB 600. Okay, so now you put different colors that you can see. You create a cloud node and then you fill in everything. Remember,
Okay, so
yes, anywhere. Remember, on itself is already strongly connected, isn't it?
yes.
Yeah, so this cloud node represents the external environment, meaning from where this flow come from, like that. So you go from C, for example, C to the cloud node. Okay.
There will be 2 arrows, right? Or
Yes, 2 arrow from C to the cloud, and then yes, correct. So how much is from C to the cloud?
700.
Why?
1,200 minus. Yeah, 1,200 minus 500.
No. Going in is 500, going out is 1,200. From C to the cloud is 1,200, isn't it?
Oh yeah, okay.
There 500, correct. Okay, next from A. again to line. Okay. So how much from the cloud to the A?
From the class to the A, 1000.
Very good, very good. Okay, and then that 150, exactly. So now from D to the cloud, you can intersect, no problem.
Oh, okay. Wait, let me intersect.
That's why you make it different colors so that you know. So how much?
From the clouds to the D is 600.
Going in,
And the other one is 750.
very good, excellent, yes. Okay. So,
Now the
yes. So now you can check in all, okay, all nodes, they are pre-matching, right? Okay, next practice. So waving section, who will try?
wait, do I have to connect the B to the
You-
clouds?
Oh yeah, you connect the B also. Yes, correct. So how much is the, oh, B no need to connect. Why? Why you need to connect?
Because it's already connected in the middle.
No, B is the system. So if you have intersection like this, the one that connect to the external, B you don't need to connect, right?
Okay.
You know the T intersection in the traffic, that the traffic come from A, C, and D are going in A, C, and D, not from B, right? So there is
Oh,
no need to connect B to the cloud,
okay.
correct? Okay, so this is already excellent. Okay, next topic, next practice. So who is, can you see waving section? So who want to try this?
I can try.
Yeah, okay, so you do. Michelle, okay. Share your screen.
Can you see my screen?
Share. Wait,
Can you see the whiteboard?
anyone can see Michelle?
Not yet, sir.
Not yet.
Now can you see?
Not yet.
Oh, wait, does it say your screen sharing is paused? Oh, wait. Now can you see?
Yes, I can see now.
Okay.
So here you have, this is a waving section. Usually in the roundabout or in the U-turn. Okay, we model it this way.
Okay.
So that is T, this is C, that is B, this is A and E. Okay. So then A to B is 100.
Okay.
Okay. B to C is 300. 300. And then C to D is 75. And then C to F is 225. And then E to B is 200. Okay, now you create different color to the cloud. From F to cloud, how much?
2 to 5.
Correct, very easy, right? So D to cloud is
75.
5, okay, and then from cloud to E,
Is 200.
very good. And then from cloud to A,
Is 100.
100. So now you check each of the node, are they equal?
Yes, they are equal.
So they are pretty much okay. Excellent.
Okay.
Okay. Okay. Next practice. Okay. Share my screen. Can you see it? Okay. Which of the following is already in IFN? If not yet IFN, how do you make it into IFN? Oh, who did not recite today? Michael. If A already in IFN, yes or no?
A is not AFN, right?
A is not IFN. Why?
Oh,
Because the amount that goes in for the nodes is not the same with the amount that goes out.
Yes. So how do you make it into IFN?
Make a cloud node.
Very good. So how about B?
It is not a IFN either because you can only go one way, not the other way around.
Right. So how do you make it into IFN?
We can just simply
Add one.
change it like the C, right?
cloud node and then
Yes.
connect it with goes into and goes out to, right?
Okay. So the same is C and D. Okay. How about E and F?
E is already ideal, right?
Correct. How about F?
Also same.
Yes. It's already
Yes.
IFN, right? Very good. So easy, yeah? So basically you already know, right? Okay, so okay, next topic is about global scaling. So this is important to calibrate, okay? So remember, ideal flow is a relative flow, okay? That means it is a rational number, right? By definition. Remember in random walk on network, we need to divide the flow with the statistic of the flow, okay? So because the ideal flow is a relative flow, it is actually scalable for the entire network. So if you have a F as a flow matrix, you can multiply by scaling alpha. Alpha must be positive of real number. Okay, so then you can have what is called global scaling for the entire network. Okay, and you can also create what is called basis network. Okay, what is this basis network? It is an IFN with the minimum integer. So how do you calculate? First, you put them into rational, and then you multiply by the LCM, okay, least common denominator, least common multiple of the denominator. Okay, first I want to discuss about equivalent IFN. So this is an important concept that two IFN are called equivalent if and only if they come from the same stochastic matrix. So global scaling will only create an equivalent IFN, right? So IFN with the minimum integer flow in all links is called basis network. Okay, now very nice properties of equivalent IFN. You can calculate the variation of the flow or the average entropy, average node entropy. They are both invariant, meaning even if you scale up, scale down, it will not change. Okay. I will show a few standard form. So there are 4 standard form in IFN. Okay. One is based on total flow. If the total flow in IFN is 1, how do you get this? You divide each link in the flow by the total flow to get this form. Second is called minimum flow in the network, is 1. That means you divide the link flow with the minimum flow to obtain this form. Okay. Next one is maximum flow in the network is 1. So how do you get this? You divide each link flow with the maximum flow. The last one is called basis network. What is this? The link flow are all integer, which is minimum. So how do you get this? A little bit more complicated, but not difficult. First, you put the link flow into fraction, okay? And then you get the denominator of those fraction. And then you get the LCM of the denominator, okay? Then you multiply, then you will get the basis network. Let's give example. So this IFN on the left, okay? What is the total flow?
1700,
No,
17,000.
the total flow is 38.
13.
On the left. Let me.
38.
Can you see? I will put in a different color. Here, what is this? This is IFN, right? You see, this is irreducible and then pre-magic, right? So the total flow is here, 38. Okay. Now, I want to scale it up to so that the total flow will be 17,500. How do you get that? Okay, so you multiply by a scaling. So you get the scaling factor. What is this, the scaling factor? 17, okay, 500 divided by 38. And then you multiply each of these. Okay. So of course, 17,500 divided by 38 is 460.5, right? So then you multiply each link with that number, scaling, okay? Then you get this flow in the right. And of course, they are also pre-magic, and the sum now becomes 17,500. Is it clear or not? You just multiply by one number. Any question? Okay. Now I want to get the basis network. Okay. Suppose this is the flow matrix that you have. Okay. And then the flow matrix, you put it into rational number, which is fraction. Okay. So if you put them into fraction, okay, you divide by, so if you put them into fraction, you will see the denominator here. Can you see the denominator? What is the denominator of the fraction?
49.
49, very good. So then you multiply this with 49. Okay, you will get this matrix. Isn't it? So you will get integer. Okay, the basis network is the minimum integer. So look at this. The minimum flow is not 1, okay? The minimum flow is What is the minimum flow in this case?
3 fraction by 49.
No, this is already equivalent.
Huh?
The minimum is 3,
Oh, okay.
not the 0. Clear, yeah? So look at this. In this network, the total flow is 1. In this network, the total flow is 49. They are equivalent networks. Can you see that? Okay. Okay, let's practice. Suppose I will hide the dummy node, the dummy link and the cloud node. Okay, so basically there is a cloud node here, right? So how much is this? 3.5, and of course this is also 3.5, right? So I will hide it. So now, can you get the basis network? Anyone who did not practice? Michael.
Yeah.
So can you get the basis network?
Uh,
What is basis network?
um,
Anyone can solve this? Anyone? Abel, Eugene, Darin, Eileen, Lilian.
I guess I can try.
Can you help Michael?
Oh, Michael.
So what is basis network?
Matrix.
No, basis network. Basis network is an integer IFN with the minimum integer number. How do you get?
So do we divide it by 2.5 and then multiply it by, oh, wait.
Put them
We
into,
get the sum.
can you put them into fraction? You need to get the anyone want to try?
I will try.
Okay, go.
So and
We already have given, okay, you can give me 2.5, 1, 1.5, 2, and 1.5 and 2. That one is 1, yeah.
this one.
Mhm.
And we multiply all by 2.
Oh, what happened if you multiply by 2? From where you get the 2?
So the number will be integer,
Mm-hmm.
and this will become 5.
Okay. Become
3.
3. This one become 3. That one become 2. Okay, and 2 again. That one become 4 and 4. Okay. So yeah, correct. So where do you get the 2?
Just guessing.
Oh no, not guessing. Okay. So if you put this, actually 5 over 2, right? This one is 3 over 2. This one also 3 over 2, right? This one is originally 1, 2, and 2. So what is the denominator in here?
2.
2, correct. So then that is the global scaling. Clear?
Okay, clear.
Easy, yeah? So the denominator is the one that first you put them into fraction, okay? And then you get the denominator. If they are different, then you get the LCM, least common multiple. Okay. So can you see this? Identify the basic network and what is the scaling from the basic network. Can you see my screen?
Not yet.
Share. Okay, I will show. Can you see it?
No, I can see, sir.
Okay, so can you get which one is the basic network? A, B, C, D, which one? They are all equivalent, okay? A and B, C and D are equivalent network. Equivalent means the stochastic matrix will be the same, exactly the same. Okay, the average node entropy will be exactly the same. The average flow divided by the standard deviation of flow will be exactly the same. Okay, so but one of them is basic network. What is the meaning of basic network? Minimum integer. Which one? Anyone?
The one with fractions in it?
No.
Right. Right. Oh, D? Wait, no, the top right one.
Yeah, B. Okay. The minimum integer is B. Look at so the scaling in here is 1. Oops. Right? Let me get the color. So the scaling is 1. Okay. In here, in C, what is the scaling? If this is the scaling is alpha equal 1, what is the scaling in here? Alpha equal 2. In here, in D, alpha equal
3.
Okay. So how about this?
1/18.
The total is 1.
Uh,
Okay. The total is 1. Okay. Anyway. So when we said basic network, okay, so the meaning, they are integer and they are minimum. Okay, next practice. Okay, again, the cloud node and dummy links are hidden. Yeah, there are cloud node and dummy links, but I did not show. So the question here is identify the basic network and find the scaling from the basic network. Again, they are equivalent IFN. Which one is the basic network? Michael, I give you a chance. Michael. Michael, are you there?
Hello.
So which one is the basic network, Michael, in this practice? Michael?
The third one, I guess.
Which one?
Wait. The bottom left one.
Bottom left. Bottom
Wait.
left. Why? Why bottom left?
So the
Basic network are all integer, and the integer are minimum. So which one?
so the lowest one, right? The minimum.
The lowest one is the minimum. Which one are all integer? So I will keep name, huh? This is called A. I'll give name A, B, C, and D. Which one? A, B, or C, or D, Michael? Is C? No, right? Because that is 0.5.
Okay.
B is integer? No, because
No, because 0.3.
3.
Oh, so the
Okay.
integer is the number bullet. So A.
Yes, A and D are integers. Which one is the minimum, A or D?
A, the lowest one.
Correct. So this one is the basic network. Okay.
Okay.
Clear, na?
Okay. Okay.
Okay, very good. Okay. So, if you are equivalent IFN, okay, the coefficient of variation, which is the standard deviation of flow divided by the mean of flow, is always the same. Okay, scaling will not change. The same thing with the average node entropy. This is how you calculate the average node entropy. So you get the stochastic matrix, you learn that, okay, and then you multiply by that S. Okay, you sum, double sum here, and then you divide by the total number of nodes. Okay, this is the average node entropy. They are also the same. Okay, regardless your scaling, it will not change. Okay, so this is the example earlier. So I hide the dummy node, the dummy links and the cloud node. Okay, you can see that the coefficient of variation of flow, okay, the average is different, standard deviation is different, but when you divide the standard deviation divided by the average, okay, then you get exactly the same coefficient variation of flow. Can you see that? So if you have equivalent IFN, the coefficient of variation of flow will be exactly the same, regardless your global scaling. Any question here? So next, I want to discuss about the IFN computation. Okay, so let's do IFN computation manually. So how do you get that? Okay, first you set any node as origin, and then you set 100 flow into or out of the node origin. And then, okay, when a node has only one in link and one out link, the same amount of flow will continue, right? When a node has more than one in link, the sum of the flow of in link, okay, so will be exactly the same as out link. And then you distribute the flow based on the probability distribution that you have. Okay. After that, if you want to make it integer, you divide by the minimum or the what is that? The LCM of denominator. Okay. I give you an example first. So you have this network. Okay. So first you assign from 5 to 100. And you see, I assign this 100. So let's assume the probability distribution are equal. So in node 1, okay, because they are equal, so I have 50 and 50. Clear? In node 2, because they are equal probability distribution, so I have 25 and 25 here. Okay. And then in node 3, again, because I assume equal, so I have 12.5 and 12.5. Okay. And then in node 4, because there is no other branch, right? So it continue become 12.5. So if I want to get the basic network, I divide everything with the minimum. What is this? 12.5. Okay. So I get this is the IFN. These two are IFN. Okay. So E and F are already IFN. So, but the F is the basic network. Any question here?
No.
So it's like maximum entropy, basically.
Yeah. So let's do it. Okay, let's try. So, maybe this is complicated. Let's do it on your own. So, can you draw any network that you want? Anyone want to try? Can you draw any network that you want? Share your screen. Anyone want to try?
Sure.
Okay, sure. Okay, let's try. Okay. You can put 4 node, 5 node is up to you. Okay. Okay, put them together in one node. Okay. Come back. And then, oh, okay, very good. So you keep names so that we can talk clearly. So A, B, C, D, E, and F. So first you define the probability distribution. Okay, so from B to C and B to D, are they equal or you want to send any number?
Let's just assume it's equal.
Okay, let's assume 50-50, nah?
Yeah.
Okay, and then how about C, F, and CE? Can we make it different?
Let's just say 25 and 75.
Okay. Okay. Let's put any number in AB. You want? Put 100 there. Okay. Then BC become
50.
50. And that one also 50. Okay. And then say 25% go to CF. Right? That become 37.5. Okay, that one it become another 50. And then how much is that? Now become 87.5. And then one become 12.5. When you check in A, is it the same as 100 or not?
Yep. 87.5
exactly the
plus
same.
12.5.
So you get the ideal flow network. Easy, right? Yeah. So you can do it manually. Okay.
Okay.
Okay. Anyone want to try again your own network? Challenge yourself. Come on.
I'll try.
Okay. Okay. You delete that and then you create your own. Wow, very complex. Okay. Arrow, you draw the arrow so that we know the direction. Okay, and then another node. Oh, come back to the origin. Yes.
So
Can you make it more a little bit more complex? Say from the keep name first so that I will. That one A. Okay, 1, 2, 3 is okay. Seven, 8, 9, 10. Okay. So can you make it a little bit more difficult? So from 4 to 6, okay, you add. Okay. So where's my okay? My question to you: from 4 to 6, what is the probability distribution?
50-50.
You want 50-50. Okay. Okay. How about 1 to 2 to 4?
This is 50 and then 25-25.
Okay, good. So then you start to set any flow, okay? Say 100. One, you set 100. Okay, so you put 10 to 1 is clear, right? 100 there. From 10 to 1, okay. Okay, now 2 to 5, how much?
2 to 5, still same.
Correct. And then 5 to 9 is 50. 9 to 10 is 50. Okay, how about 3 to 6?
This is 6-25.
Okay, still 25. What is the probability distribution to 6? 50-50? 1.5, right? And then that one is 12.5. And then that one is 0.5. Okay, very good. And that one is, that one is 50, correct. And then check in note 10, in and out. Yes, the same. Very good. Yeah. Excellent, Darin.
Okay.
Okay. Is it difficult or not?
Not difficult.
Not difficult at all. Okay. Easy, right?
Yeah.
Okay. So I have a little bit more difficult here. So anyone dare to do this? Lilian, probably. So the distribution is all equal. Anyway, I will just show the result. Okay. So the one that you just did is very simple network. Okay. When you have two ways, then you start to create a problem. Okay. Why? Say you start with assigning DA equal to DE. Can you see this? Can you see the network?
Yes.
Okay. So if you set the DA equal to DE equal to 100, okay. In node A, you can get all equal. So 25, 25, 25, right? But the problem is in node B, you don't know CB. So if you don't know, then you assume X. Okay, so you need to create variables. So this network is a little bit more complicated. So if you don't know, then you assume first X. Because you know the probability distribution, okay, then you calculate that. You can say that CB equal to CD equal to CE, which is equal to X. Can you see it or not?
Yes.
Okay, and then from here, okay, then you get the BC equal to BD equal to BE. Okay, what is this? This is equal to, can you see in the node B, equal to 25 plus X, right? Divided by 3 because you have equal probability distribution. Okay, but in node D, you still don't know ED. So then you assign equal to Y. Okay. Then you calculate like this. So you basically you solve an algebraic equation of two numbers, X and Y. Okay. So once you calculate the X and Y, then you can get everything. Is it clear? So yes, in a simple network, it's simple, but if once you have two ways, okay, then you start to have a problem, then you calculate algebraically. But if you have many, okay, then you need software, right? Of course, you can calculate by hand, but it's too long. Okay, that is what I developed. Okay, so the software is just to compute the based on IFN. Okay, so what do you want to compute? Is the limit distribution pi, okay, such that the stochastic matrix S U transpose minus I times pi equals 0, subject to constraint of this J times pi equal to kappa. Kappa is the total flow that you set, okay, and of course the pi must be larger or equal to 0. So the solution, hey, you remember I give you assignment of this, remember? Markov chain.
Yeah.
Yeah. So I give you assignment of this, right?
Yeah. On the spreadsheet, right?
Correct, correct. This is exactly the one that you did, isn't it? Okay. The solution of this optimization is this one. Okay. So all you need to do is from here to this last equation, which is so simple. Okay. Very easy. This is just multiply by the J transpose, and then this is the element-wise multiplication. This symbol is Hadaman product. It's just element-wise multiplication with the stochastic matrix. Then you will get F. Okay, so remember, okay, I give you the big picture. A while ago, from F, you can get the stochastic matrix easily. You just divide by the sum of row. Now, this formula is from the stochastic matrix, you can get the F. Okay, so basically now you get an inverse function. From the stochastic matrix, you can get the flow. From the flow, you can get the stochastic matrix. Okay. So the computation, I don't want to discuss again because you already learned about this. Okay. So this is the example. So if you have this stochastic matrix, you calculate, okay, and you basically get the generalized inverse, right? Like what you did last time. And then you get the node vector matrix, and then you multiply. Okay, using this, you multiply, you will get F. Okay. If you want to multiply by yourself, you can do it. You can practice on your own, but there is software to use, so you can just use it. Okay. You can also use Excel to solve this. Okay, let's practice in Excel. Anyone can practice in Excel. Did you install the add-ins?
Not yet.
Okay, you download and install the add-ins. Just double click. So I open Excel here. Okay. So if you have your add-ins installed, you go to Excel options, add-ins, go. You must have this one, ideal flow. Then you click OK. Okay. To check if it is installed already, you click any cell and then you do right click. You will have a menu here. Can you see it? Menu of ideal flow. Okay. So, and I can create a random example. So this is my random example. Okay. Using this random example, I can calculate directly the flow and so on. So there's a setting here. So where is your input location, the output location? Is there any factor that you want to, scaling factor that you want to put? And then this is the form that you want to create. Yeah? Minimum flow is equal 100, or maximum flow or total flow, okay? Or minimum integer. This is the basic network, right? Okay, so setting from E to E, correct? So let's calculate. There, you get the basic network. Can you see it? Can you do it on your own? So if you don't want the automatic version, you can also do the function. So I can, you put equal here. So I will close this. So I put equal, for example, capacity to ideal flow. You will have menu here, capacity to ideal flow. This one. Okay, and then 1, 2, 3, 4, 5, right? So F2, shift control enter, there you get exactly the same. Okay, of course, the total is the kappa. It is 23, right? So say you don't want the become a basic network, but say you want to have a certain number of the total flow. Say your total flow is how much? Say 46, for example. Huh? So I will do that. So I change this, become 46. Okay, again, F2, edit, Shift Control Enter. Yes, I get 46. The total flow. Okay. Anyone want to share your screen so that I will know how you're doing?
I'll try.
Okay. Right click. Can you click in any cell and then do right click?
Hmm?
Oh yes, you did. You did install. Very good. Okay. So you can put the settings. Settings first. Setting. Top.
This one, right?
No, the left top. No, that's correct already. Sorry. Come back again.
This one.
Yes, you do right click. Ideal flow.
Settings.
Yes. Click and setting again. The left top. Yes. So check that the input location will be correct. B8. No, it's not correct. So B2, right?
This
yes.
one.
Yes. You need to you can put the whole thing, the whole matrix if you want. Okay. And where will be the output? The output you can put somewhere. Oh, a little bit farther if you want.
Why not change?
So that you can see the difference. So that otherwise it will replace. Say you put it in M or in column M or in column K.
This one.
Yeah, okay. Output. Okay, then you click calculate. No,
Cannot.
input location you did not change yet.
Okay. Cannot change.
Cannot change. Anyway, so let's do it by function in that case. Let's do it by function. So you go to I2.
I2.
Okay, you put it equal. So you type C. Okay, capacity to ideal flow. Double click. Okay, then you do that. Okay, very good. You close it, enter. Okay, now you highlight from E to, what is the size there? 5? So yes, from E to M then. From E to,
from E2.
no, you put your cell in E, yes, and then, yes, until M, correct? And then you press F2. Function F2, correct? And then press together, Shift, Control, and Enter.
Shift, Control, and Enter.
Yes, you get it.
Okay.
Okay, so you get the ideal flow. You check the total, you get the sum. Yes. Okay, good. So very good, Darren. So anyone want to practice on your own?
I'm confused how to install the ideal flow.
Yeah, you can just install by double click.
Double click
Yes,
the XLAM.
correct.
Oh, okay.
Anyone want to share your experience? If you have trouble, so I can help you.
I still can't install it.
Oh, it's already installed.
It's already installed. I
Yes,
don't see it in add-ins though.
Oh, you did not see in add-ins. Did you double click it?
Yes, I did.
And then you go to add-ins, option add-ins.
Oh, wait.
You want to share your screen so that I can see?
Okay. Wait.
How about the others? Eugene, Eileen, Michael, Lillian?
Oh,
File options, add-ins.
this is after I.
Yeah.
This is the Excel I double
Yes, yes.
click.
So it means again, you double click again, probably. Okay. You need to trust the macro. Oh, where did you get? Ah, you get it from the, no. Can you get it from Moodle?
Oh,
This is the old version that you,
oh, this one.
yes, yes. Was it there?
It's still not there.
Okay, so if not there, let me check. This is a little bit. If not there, you can actually put the XLAM by yourself. So wait, yeah. George. I will share to you the actual location. When you do an add-in double click, what you are doing is actually putting into, let me share my screen so that you will see. So this is the actual folder that you put the add-ins. Can you see?
Wait, I have to stop sharing.
Okay. Can you see my screen? So yours will be users, probably your name, Abel, and then app data, roaming, Microsoft add-ins. So this is the name of me will change with yours. Right.
I don't have an app data file, app data folder, I mean. Wait, yeah.
Okay, app data, roaming, Microsoft. So you put the XLAM in this folder and then it will work.
How do you find the app? I don't have an app data folder.
Okay, show me your screen then.
So users
Yes,
is only
users,
user.
yes, and then you just type up data roaming Microsoft admin. After that. Oh, no. User, correct. Update and then row.
Ah,
Okay. You have, but Microsoft hide it from you. Okay.
so
So you just copy that exclam there. Yeah.
I see. And it should
Okay,
appear
so
here then.
yes. So
Oh, wait.
otherwise you browse. You can browse. If not working, you can browse. Go to add-ins again. Add-ins, go, and then browse.
Ah, I see.
Okay, good. Then,
Okay.
okay, so you have it. You can check one. You can click any cell and right click. There, the ideal flow is there. Okay, so you can create random example. Random example first. There you got it. Okay, very good.
Okay.
Okay, no problem, right? So,
Thank you.
still have problem? Eugene, Michael, Ellie,
No, I got it. Yeah.
you got it. Lillian,
I'm still trying to find the files.
okay. You want to share your screen so that I can help you?
Oh, okay. So I should go to users, right?
Okay, users, correct. And then, or you can go to add-ins directly. Wait, go to Excel. Okay, did you download already? Okay,
Yes, I've downloaded.
okay, more. Add-ins, go, and then browse. Go to your download a while ago. Where is your download? Download.
Oh, wait.
Oh, you did not download yet.
I've downloaded, but wait.
Where did you download it?
I've downloaded.
You just double click that. So you browse and then go to that file, and then it will work. Not yet. Again,
Oh,
this is browsing.
okay.
So go to that file. There, you click that on click OK.
Oh, okay.
Okay. Then you right click.
Okay.
The ideal flow is there, random example. Click random example. Then you have it. Okay, very good.
Okay, thank you.
Okay. So Michael, did, Abel, Eugene, Eileen, is there any problem?
No, sir.
No problem.
I don't have an isolate meter. I'll do it later.
Okay. So
Okay.
if you want to do it later and you have problem, you can just contact me, huh?
Thank you, sir.
No problem. Okay.
Yes, mine too. I will be doing it in another laptop later on
Okay.
because
Okay. So,
the Excel is not working.
okay. Okay.
Thank you.
So, okay. So I will continue then with the slide. So I give you the software, so basically computation is no problem, right? Okay. Another way to compute is actually using maximum entropy. Okay. So to define it, okay, you have what is called node entropy. For each node, you calculate for each node I, you calculate the entropy, and you know the total flow. Okay, then a network entropy is defined as the average of the node entropy in this case. Okay, so if you look at this formula here, which I'll put color. So if you look at this is the entropy of node I. Okay, so I put this here. So this is basically HI. Okay, and then what is this? This is the node flow divided by the total flow. So this is basically the probability of each node. Okay, then you sum of all of that, meaning this is the average of the node entropy. So using this average of node entropy, you can define the ideal flow. Okay, so of course subject to constraint. What is this constraint? This is the sum of stochastic matrix must be 1. That is the definition of stochastic matrix. And what is this constraint? This constraint means the sum of row equal to the sum of column, right? So this is basically pre-magic. Okay, and the total flow must be defined. So you need to have a parameter called kappa, which is the total flow. Okay. So now if you use Excel, you can also compute. Okay, you can calculate the entropy using the Atkins. The entropy is computed directly, right? So given the stochastic matrix, you can calculate the ideal flow. Easy. Okay. So you want to practice using your Excel? Okay, can you find the basis network of this? If I give you the outlink probability, can you get me the basis network?
Yes.
Yeah, this is the stochastic matrix is given, right? Okay, so try to use Excel to solve it. This is the answer. Okay. So, okay. Next one is the calibration. Okay, so yes, you can calculate the what is that? The IFN, right? But what is this for? Unless you can calibrate it for your real world data, right? So this is how you compute the IFN for the real world data. Okay. So if we know certain link flow data, okay, then your goal is to find the global scaling. So I put global scaling with this notation. Okay, this is the notation of global scaling, so that you calibrate your model to match with the observed data. Okay, so suppose I use this notation with W represent the observed link flow from the real world. W mean real world, okay, of link K. And then I have another notation here. What is this? This is the model link flow for the given global scaling C here. Okay. Now, when you said calibrate, that means you want to find the global scaling to minimize the sum square of error. How do you get the error? The error is from the flow in the global and the scaling, okay, and then you square it, and then you sum of all links. Okay, so I give you an example after this. So we only match the link with the observed data. Okay, link flow without observed data will be automatically calibrated based on the inference of the link flow with the data. So I give you an example here. Okay, say I know that link CD is 900. Okay, so CD is this one. I know here is 900. So based on the actual observation on the link, this is supposed to be 900. What is the global scaling? Can you get?
1 or 3?
The global scaling is 900 divided by 3.
300.
Yes. Right? See, the global scaling is 900, the one that you want, right? And then divided by the 3. 3 is the model, right? So you see CD is 3, right? So, but you want it to be 900. So then 900 divided by 3 is 300, okay? Once you get the global scaling, that's easy, okay? So you multiply everything with 300. So for example, A, B here is 3. So multiply by 300 is 900, right? 2 here multiply by 300 becomes 600 and so on. So you get this, the new network after global scaling. So you check if it is correct, okay? See, this one supposed to be 900. The error is 0. Is it clear? Up to here. If you have only one link flow, okay, then you get the error is 0. Any question? Okay, let's go to the next one. Okay, a better way to calibrate the IFN is to find a global scaling that maximize, okay, the R square, like a regression. You learn regression, right? So what is R square? R square is 1 minus SSE divided by SST. What is SSE? The sum square of error a while ago, the one that we discussed a while ago. So this is the SSE. Okay. So what is SST? SST is the real world data flow, minus the average flow of the real world. And then you square it, and then you sum of all links that you know. Okay, the feasible region of R square will be 0 to 1. Okay, so R square of course can be negative, you know. So what is the meaning of R square negative? That means this SSE divided by SST is larger than 1, right? That means probably there is a conflict in the data or in the model. So the larger R square nearer to 1, that is better. Okay, so let's give example. Say we know a while ago was only link CD, right? This is 900, right? So now I have two observations, okay? I know this is 900 supposed to be, and I know that BC here is supposed to be 500. So find the global scaling so that I will know other flow. Okay, so to get the global scaling, okay, so we get for each of them, okay? So BC supposed to be 500. The basis IFN is 2, okay? CD supposed to be 900. The basis IFN is 3. Okay, so then you said, okay, this is the scaling for BC is 250. Okay, the the scaling for CD is 300. Then you say, oh, maybe the global scaling is average of them. Okay, which is 275. Okay, so then this is our first try. Okay, and then you get the average observation. Okay, is 500 plus 900, right? And then because you have only 2, so become 700. Okay, next. Then if you try using 275, okay, then the flow of the scaling will be 550 in BC and 825 in CD. And then you calculate the error. Okay, from the error, you square them, you get this value. And then you calculate the SST. What is SST? The observation minus the average. Okay, this is the observation minus the average, and then you square them. Okay, and the R square is 1 minus SSE divided by SST, which is earlier, it is 8,125 divided by the SST is 80,000. So you get 0.89. Okay. Oh, it's quite good, right? But this is not the optimum. Okay. If you want to get the optimum, okay, so you search one by one, okay, and then you will get actually the optimum one is this one. The optimum scaling is 285 and R square is 91%. How do you get the search? You do it one by one. So you scale for each, okay, scaling, and then you graph that, and then you get the minimum of the SSE or the maximum of the R square. Okay, so the maximum of R square is here. Oh, this is the minimum. So then you get the value with this 91% here. Is it clear? So after you scale, okay, you multiply everything with the global scaling. So this is the final result. Okay. So in this example, you have three observations. Okay, AB is 450, BC is 600, and this one is 900. So if you multiply, if you get the global scaling, okay, as before, you will get negative R square. Okay, if you calculate, you will get negative R square. Why? You can see the SST compared to the SSE is actually much larger than 1. Yeah? The SSE divided by SST is larger than 1. So it's negative. So in that case, there's a problem with your observation. Okay? Whatever you put here, this is example of the proof why your data is invalid. Whatever you put here, it will not satisfy the pre-magic constraint. So in that case, there is something wrong with your data. So look at this. IFN can check whether your data is actually valid or not. Okay. So if you want to make it the conflict to be correct, then you can get this technique. Okay. So for example, you set certain values. Okay. So for example, the corrected value is 400 in here, then it will become consistent. But of course, this observation is not unique. So you can set any numbers as long as it is valid. Okay. So that's all the theory that I can give you. So let's talk about the application, okay? So this is example of application of IFN to check the congestion in a row. Okay, so for example, you want to add or remove one link at a time. Okay, and let's assume that all links have equal capacity. So in this case, the flow is identical to congestion. We want to ask, okay, what will be the effect of adding link to congestion in the network? Will adding link reduce congestion or increase congestion? Okay, and which link should be added minimally to reduce the maximum congestion? I give you an example. Suppose I have this network in A. This is very simple network, right? And calculate the IFN. Okay, so because this is simple, so everything is 1. So I add a network, in this network, link 2, 5, and then I calculate the IFN. What is the maximum congestion here? 2, right? This is the maximum congestion. And then I add again, link 1, 3. This is, I add link 1, 3. Okay. What happened to the maximum congestion here? Oh, this link 5, 1 become 4. That means adding one link actually increase the congestion level somewhere else. Right? From here, I say, what is it really increasing the congestion level? Let's say from here, okay, I go to D. I add another link here. Okay, 2, 4. And then I calculate the IFN. Wow, again, increase the congestion level. Okay, the maximum congestion level now become 6, right? See. Okay, I add link 2, 4. Okay, when I calculate the IFN, you know that there is congestion somewhere else, not near, very far. Okay, the adding link is 2, 4, not 2, 4. Okay, and the congestion that increase is in 5, 1. Right? From here, I want to reduce the congestion. What happened? So I add another 2 possible links. Okay, one is this one, and another is that one. So E and F. Okay, so in here, if you compare, if I add this link 4, 1, the other one is I add 3, 1, you see that this is better. Okay, the maximum congestion here is 3.5. In network F, the maximum congestion is 4. So adding 4, 1 from network D is actually better than adding link 3, 1. Can you see? So imagine this adding is actually like tollway. Okay, you have a network, you add a tollway. Okay, will adding a new link create a better in terms of congestion or not? Okay, not necessarily, right? So there are certain links that you can add will actually reduce. If not, you can actually increase the congestion. So using this ideal flow network, you can actually check which links should I add, which links should I reduce, and so on. Okay. So this is just one of the example. Okay. you can read by yourself, okay, the other example of application here. Okay, you can find the optimum link that if you add will be the greatest reduction of maximum flow. Okay, and you can also use the IFN to do long-term prediction. So I want to know when and where the traffic congestion will happen based on certain policy scenario. Okay, so in this case, the policy that I want to simulate is adding one lane on the most congested link when the maximum congestion already 0.9. Okay, the network does not change. Okay, and we have this all assumptions of the numbers. Okay, and the model. So you see here, this is the base scenario is year 2000, and after I compute, okay, based on the global scaling, you will see that I will know which link, okay, will reach the maximum congestion and in what year. Okay, so in that case, I can estimate space and time using IFN. Okay, so this is just a computation that you can check on your own. Okay, and what is the maximum congestion link are also listed here. Okay, so this is another example of people always think that to improve the congestion in the road network, you want to add the lane, right? So you always widen the road, but this is actually a myth, you know. So traffic congestion can be improved also by reducing the number of lanes, but if you know where. Okay, in this example, okay, so I want to reduce the lane capacity, okay, in link AC. Okay, first time the congestion level is 0.85, the maximum. When I reduce the number of lanes from 5 to 2, you observe now becomes 0.8. So it actually improved, okay? Congestion level is improved not by increasing the number of the number of lanes, but actually by reducing the number of lanes. So this is where the IFN works for you to think. And IFN can also be applied to other field other than transportation. Okay, I applied this to data science, so we can also do supervised, unsupervised learning, and so on. Okay, so I think time is up. So is there any question? So using the IFN, you can also find the ideal lane capacity. Okay, so you can also get where the mass equilibrium is exactly the same as Pareto optimal. And this happens when the capacity matrix is actually pre-magic. Okay, try this network. Try this example, okay? And I will give you this as your assignment. Okay, so I give you capacity matrix. This is the number of lanes. Okay, and I want you to calculate so that you will see how the traffic will be improved, not by increasing the number of lanes, but by reducing the number of lanes. From 7 lanes here, I reduce it to 4 lane, and the maximum congestion will improve from 0.87 to become 0.7. Okay, so this will be your assignment.
Is it using solver, sir?
It's up to you. You use solver, you use add-ins, it's up to you. Okay, if you use add-in, you can do this in less than 2 minutes anyway. Okay, it's just practice so that you can know what to do. Okay, so this is another example of standard test, which is called SIOPS network. This is the city that we have, and we computed the ideal flow. Okay, and of course, because the total flow is clear, so this is the real world compared to the ideal flow is exactly linear. And this is another example in hypermarket in Surabaya, this one, right? So this is in Pondok Chandra. Okay, this study was done long time ago. Okay, and
So how does this work? So they make, what are the points?
okay, good question. So these are the inventory survey. Okay, so this is the hypermarket. You see the entry and exit there. Okay, and then what we did is to ask in the cashier, after the cashier, we asked the shopper, where did you pass? Okay, can you draw? Okay, so we draw the trajectory. Each person we draw trajectory here. Okay, oh, I pass here, I pass there. Okay, so this is using questionnaire. And then after that, we get the network. Can you see this? So the network, we just assign any node name. So 1A, 1B, and so on. So this is the student who did this. So we have 88 nodes and 139 links. Okay, everything is 2 ways except the cashier. It is 1 way, right? And then we assign that trajectories of the customers into the network. Okay, so you see this example here at the bottom. I put there that say pedestrian number 160. So we have actually only 256 probably customer for the survey. And this is the trajectory that we assign. Okay. So you see that from 1A to A, then to B, then to D, and so on, the trajectories. Yeah? And then from the trajectory, of course, you can get the flow, right? Okay. So this is the flow which is not pre-magic. Okay. And from there, you can put it into ideal flow. It will automatically correcting, okay, so that the flow will become pre-magic. Okay, so and then you can compare the real world flow, which is from the questionnaire, and the ideal flow. Okay, and you can see the error here, the one in red.
Wait, so what's the goal here?
Oh, the goal is actually to see this. Okay, this is the flow pattern. Okay, so this is like a business intelligence. So you want to know where is the customer going, and then what things they want to buy and they don't want to buy. You see in here, you can see that there are so little people buying furniture and bed cover, and most people are buying bakery, right?
Yeah.
So from the flow pattern here, you can see, okay, and then from here, if you want to join with the supermarket, then you can say, okay, let's change the location of the bakery somewhere else, okay, near the furniture, for example. What will happen? The flow will change, right? The flow pattern will change. And then you will see actually the layout of the supermarket will influence the flow, and it can change the profit of the supermarket. Can you see it?
I see.
So,
Sadly, we cannot join with this supermarket anymore since it's closed.
oh, really? It's closed already.
It's closed already. It's like
Okay. Yeah, a long time ago. This is like 2007 when I was still.
oh yeah, it's already so long ago. So
Yes, yes. Study is very long.
it's
So,
near my
yes.
house. So yeah.
Yes, yes. So this is the calibration. So you can see the comparing the ideal flow and the real workflow, and then you can see the distribution is almost the same. And also you can get the SSE here, and you can see the minimum SSE. Right. So this is the campus network in the Philippines. So, and they want to add a new link here. You see the difference in 55 and 63. This is against the forest. So the campus is very big, like ITS or University of Indonesia, very big. So it's like 80 hectare land. So there is a forest in the middle, and then they want to create the road, okay, either one way or two way, and we analyze that. Okay, and this is the result. So the base scenario is the current road network, and then what will happen if we have one way and we have two ways, okay, and what is the travel time distribution, delay, and so on. So this is the example again of the whole Metro Manila. Okay. From Google Map, we can also get the IFN and the congestion for the whole entire city. Okay. So you can see, we can zoom in, and then you can see where is the possible congestion problems. So for application of transport application, so for example, what will happen if you reduce the parking, for example? Okay, you add parking or remove the parking, okay, or you do a road widening, or you add certain bridges, or what happen if the night market occupy the whole street. These are the practical application that you can use in ideal flow network for transportation. Or what happen if you change the direction, and so on. Okay. So there are many videos that I posted in YouTube, so you can watch on your own. Huh? So until here, is there any question?
I would like to ask, like, for a meeting
Yes.
for the group project.
Sure, sure. You can just text me, and then we can set appointment. Is that okay?
Okay.
Right.
Okay.
Yeah. I think a Thursday afternoon, maybe around 5. Is it okay?
We have a class.
Oh, you have a class. How about Saturday?
I'm good with that. Eugene, Rodney.
Oh, Saturday afternoon.
Okay, Saturday.
Saturday I have a meeting. Wait. Tomorrow is fine.
Tomorrow, what time?
Tomorrow
Tomorrow,
morning.
what time?
Morning. Or today
Morning.
evening is fine.
I prefer tomorrow morning.
Okay, tomorrow morning.
Tomorrow morning.
Tomorrow
Morning
Please wake
is
up, Rodney.
10 a.m.
Eugene, actually, yeah, Abel might have Like his
I'm at 3 p.m.
yeah, his
That's
not morning.
no.
Oh,
Okay.
you have another event, Abel.
Yeah.
What you can
At,
do?
at,
I
at
have
3
meeting
p.m.
tomorrow afternoon, so morning and
Yeah, morning.
Yeah, tomorrow morning will be good.
yeah, okay. 9 o'clock maybe. Fine.
Okay.
Okay, okay.
Yep.
Okay.
Okay.
Oh, send me your Zoom link then.
Or the Zoom link.
Yeah, you can just send.
Oh, so we book the room.
Yeah, you book the room.
Okay.
Okay.
Okay, thank you, sir.
Thank you. Okay. So
Thank you.
next meeting is June 8th, right? So that is the final meeting. So you present your group project. And of course you need to finish everything before that, right?
So we have no meeting next week.
Next week is
1st of June. No.
1st of June is Pancasila Day, it's holiday, isn't it? You want to have a meeting?
That's a thing. Okay. Yeah. I see.
I'm okay if you want, but
We'll see.
okay.
We'll think about it.
Okay.
Okay.
So our last meeting will be June 8th. Then final exam.
I see.
Okay.
Okay. Okay.
Okay. So if you have problems, so you can contact me via WhatsApp or Facebook Messenger. Huh?
Okay.
Okay. Good.
Thank you.
Thank you for
Okay.
today, sir.
Thank you for today. Yes.
Thank you, sir.
Thank you. Bye bye.